Welcome to the Blueprint, where we explore the massive structures that reshape our landscape. Today, we are focusing on the hidden physics and high-stakes maintenance of dams. While they appear as immovable sentinels, they are constantly battling the silent force of water, attempting to move underneath them. This phenomenon, known as piping, occurs when water seeps through the soil beneath the dam's foundation. If the pressure is high enough, it begins to wash away fine particles, creating hollow pipes that can lead to a catastrophic internal collapse. To prevent such a failure, engineers must calculate the stability of the soil at the exit point where the water reemerges. This is governed by the exit gradient, I_exit, and the critical gradient, I_crit. The critical gradient is the point at which the upward pressure of the water equals the submerged weight of the soil, effectively making the dirt weightless and prone to boiling. To ensure safety, we calculate a factor of safety, Fs, against piping using this formula. The history of harnessing this power dates back to pioneers like Fourneyron, whose 19th century turbine designs paved the way for modern hydropower. The potential energy these turbines capture is calculated in U.S. customary units using the hydraulic power formula. Building these giants required revolutionary materials. For the Hoover Dam, engineers couldn't use standard mixtures. They developed low-heat Portland cement. Because concrete generates intense heat as it cures, a standard pour would have remained dangerously hot for over a century. By using this specialized low-heat cement and an intricate system of refrigerated cooling pipes, they were able to set the concrete in sections, ensuring the structural integrity of the 6.6 million tons of masonry. However, once a dam is built, a new clock starts ticking: the accumulation of silt. Every river carries sediment, and when that water hits the still reservoir behind a dam, the velocity drops and the sediment falls to the bottom. Over decades, this silt builds up, reducing the reservoir's water capacity and potentially burying the power intakes. This silent filler can eventually turn a massive lake into a shallow marsh, rendering the dam useless for both power generation and flood control. To combat this, the industry relies on the massive undertaking of dredging. Specialized dredging crews use powerful suction cutters and submersible pumps to vacuum the accumulated silt from the reservoir floor. It is a grueling, continuous job that requires precise navigation and heavy machinery. By removing millions of cubic yards of sediment, these operations restore the active storage of the dam and ensure the turbines continue to receive clean, debris-free water. From the early Roman stone structures to the Three Gorges Dam, which is so massive it slightly altered the Earth's rotation, the engineering remains a battle against the elements. Whether it is calculating the factor of safety against underground piping or managing the relentless buildup of river silt, maintaining a dam is a perpetual effort. These structures are not just monuments of concrete, they are living systems that require constant vigilance to keep the lights on and the valleys safe.